of 1, 2 and negative 3, 4. First, let V1 equal to U1, then we find that V2 equal to U2 minus bracket U2 dot V1 over bracket V1 dot V1 multiplied by V1. V2 equal to matrix of negative 3, 4 minus 5 over 5 matrix 1, 2 equal to matrix negative 3, 4 minus matrix 1, 2. V2 equal to matrix negative 4, 2. Thus S equal to bracket V1, V2 equal to bracket matrix 1, 2 and negative 4, 2 is an orthogonal basis. Matrix 1 over 2, 0, 1 over 2. V2 equals to negative 5 over 2, 1, 5 over 2. Then W equals to curly bracket V1 and V2, which equals to curly bracket matrix 1, 0, 1 and negative 3 over 2, 1, negative 5 over 2. Which is an orthogonal basis.
Here, I want to teach you the Gram-Schmidt process.
He knows a lot about all kinds of stuff. Professor Dave explains.
In the previous tutorial, we learned all about orthogonal vectors and how we can generate from these a set of orthonormal vectors by taking each vector and dividing it by its length. This makes each vector's length equal to 1. And since they were already orthogonal, the new vectors become orthonormal. But what if we start with a set of vectors that are not already orthogonal? Furthermore, how do we go about making an orthonormal basis for a vector space, given any set of vectors that form a basis? We need to learn something called the Gram-Schmidt process. So let's take a look at this now. To see how this works, let's examine the vectors v1 to vn, which serve as a basis for the vector space V. Our only requirement for these vectors is that they form a basis. We are no longer assuming any orthogonality between them. The Gram-Schmidt process takes these vectors and forms a new orthogonal set of basis vectors, which we will label u1 to un. The process goes as follows. First, start by setting the first new vector u1 equal to the first basis vector v1. For the second step, take the second vector v2 and subtract from it the inner product between v2 and u1, divided by the length of u1 squared times the vector u1. So altogether, that looks like this. Then the third step will be to take the vector v3 and subtract a similar term. The only difference is that now we take the inner product between v3 and u1 in the numerator, and then we also subtract another term, which is the inner product between v3 and u2, divided by the length of u2 squared times u2. At this point, you may notice a pattern emerging. For each new vector, we must subtract an additional term that involves the inner product of the current v vector with each previously found u vector. So we will need one more such term for each vector. The reason we need to do this is that we are subtracting off any part of the v vector that is not orthogonal to the new vectors we have found, leaving only the orthogonal part. To make things a little more succinct, Each of these new vectors after the first one can be put into summation notation as follows. uk equals vk minus the sum over I from 1 to k minus 1 of the inner product between vk and ui, divided by the length of ui squared times ui. If this notation is unfamiliar, go back and check out some of my tutorials on sums. Otherwise, we can quickly see how the orthogonal basis we just wrote can be derived from this expression. Some useful tips to help remember how this looks include noting that the only v vector that appears in the formula has the same number as the u that is being found. Also, every other u vector that has already been found will show up in a specific term in the remaining v vectors. Another helpful feature is that u1 has one term in its formula, u2 has two, u3 has three, and so on. For ordinary real vectors, what we mean by inner product is simply the vector dot product. And recall that the length of a vector is simply the square root of its dot product with itself. So just considering this case, we can rewrite these terms with dot products. This might all look a bit overwhelming at first glance, but let's look at an example and take it step by step. Consider the basis vectors for R3. v1 equals 1, negative 1, 1, v2 equals 1, 0, 1, and v3 equals 1, 1, 2. We always start by setting our first vector u1 equal to the first basis vector, so u1 equals 1, negative 1, 1. Now we get to step 2, where we take our second vector v2 and subtract v2.u1 divided by u1.u1 times u1. Well, v2.u1 will be 1 times 1 plus 0 times negative 1 plus 1 times 1, or simply 2. Then u1.u1 will be 1 times 1 plus negative 1 times negative 1 plus 1 times 1, or 3. So u2 equals 1, 0, 1 minus 2/3 times 1, negative 1, 1. Simplifying this expression, we get u2 equals 1/3, 2/3, 1/3. Finally, for the third vector, u3, we will take v3 minus v3.u1 over u1.u1 times u1 minus v3.u2 over u2.u2 times u2. Now simplifying, v3.u1 is 1 times 1 plus 1 times negative 1 plus 2 times 1, which is 2. We already know that u1.u1 is 3, so let's just use that. Then v3.u2 is 1 times 1/3 plus 1 times 2/3 plus 2 times 1/3, which equals 5/3. And then u2.u2 is 1/3 times 1/3 plus 2/3 times 2/3 plus 1/3 times 1/3, which becomes 1/9 plus 4/9 plus 1/9. This is 6/9, which simplifies to 2/3. Plugging in all these dot products, we get u3 equals 1, 1, 2, minus 2/3 times 1, negative 1, 1, minus 5/3 over 2/3, which simplifies to 5/2, times 1/3, 2/3, 1/3. Lastly, going through the vector addition, we end up with u3 equals negative 1/2, 0, 1/2. These three vectors form an orthogonal basis.
Today we're doing some linear algebra. Specifically, we're going to be finding an orthogonal basis spanned by a set of vectors. And at the end, we're going to take a look at how to find the orthonormal basis. This is going to be an example video, not too much on concept, but I'll kind of So here's a typical problem you might come across. So you want to find the orthogonal basis, and we have two vectors here spanned by that set of vectors. But first, the way you're going to want to approach this is something called the Gram-Schmidt method. And the Gram-Schmidt method is basically when you have two vectors pointing in some direction that are perpendicular, you can make them perpendicular by using their components. So the process, I'm just going to kind of go out here and and say a little bit more. So a vector has its components, right? If you take the projections of those components, which acts like the shadow of the vector on the coordinate system, you can find the combination that can make the vectors orthogonal, or perpendicular. So this is kind of the method in doing so. You subtract the components off. So you take the projection of v1, which is we're defining as the first vector x1 here, and you subtract it off. And the way you do that is by doing the dot product. And another way of writing the dot product is simply doing the transpose, because that's what's great about linear algebra. The transpose of a matrix acts as the dot product. So we're taking the vector we want to project it on, like that shadow, and we're going to find the perpendicular portion. So, and that's if you have two vectors. Now what if you have three? You would take the third vector, you would subtract the projection of the third vector from the first vector, and then also from the second vector as well, and then you would get that as well. Again, dot products here, and then we can rewrite those as transposes. So become familiar with the Gram-Schmidt method in terms of the formula. This is one formula of doing it. There is a few other different ways of writing it, but definitely look online and see more of the concept. But we're just going to go over the examples now. So first thing you want to do when you solve this problem is define v1 as x1 by using the Gram-Schmidt method. Next, we're going to want to solve for v2, which to make the mathematics easier, we're just going to write it in this form in the transpose because it's easy to calculate. So we write x2, which is our v1, we write our x2 first, subtract the transpose of that, so all you do is make the column into a row. So we do that, and then we multiply that by v1, which we define as x1, so we just write x1 there. Then we do v1 transpose, which is just the transpose of x1, and multiply that by v1, which is x1, and all that times v1 again. Then you're going to do some math here. So just some simple matrix multiplication. So you should get 15 over 30, but that would be 4, let's see, it would be 8, so 4 times 2 is 8, negative 1 times negative 5 is 5, plus 2 would give you 15, and then we get that over 30. That's a scalar there. Multiply it by the vector, so we can say 15 over 30 is 1/2, so we'd rewrite that, make sure, and distribute the 1/2 as such. So then all you do is subtract the two vectors. Pretty simple, 4 minus 1, so on and so forth. So you should get 3, 3/2, and 3/2 again. Now that's our v2. So the orthogonal basis is simply the span of those two vectors, because now these are the two perpendicular portions, and you can test that as well by taking the dot product. So now you just write it so some arbitrary orthogonal basis w is the span of those two vectors, so v1 and v2. And that's how you find the orthogonal basis. Now if you want to find the orthonormal basis, all you got to do is take that span of vectors and divide by its magnitude to make it a unit vector. So this is v1, remember this is v2, so we just take the square root, or the square of each component, and then sum them all up and square root them, so 2 squared, negative 5 squared, 1 squared, and we should get radical 30. Do the same thing for v2, you square all the components, and then you should get radical 6 here, and all you do is divide each part by the unit vector. So just to make life simpler for now, we can actually rewrite that v2 as 2, 1, 1 to make the division a little easier here, because if you divide that whole vector by 3, each component by 3, you get 2, 1, 1. So here's the orthonormal basis. Here it comes. So we'll just call it b equals the span of 2 divided by radical 30, negative 5 divided by radical 30, and 1 divided by radical 30. Remember, just dividing each component by its magnitude, and then we do the same thing for the other side. That's why I made a little note over there. So that's how you find the orthonormal basis. This is a good example to be used. By the way, it's a note here. If you had a fourth vector, you would also subtract the projection of v3 on x4. So this could keep going on forever and ever, but generally these problems take quite a long time, especially when you get to v3. So just thought I'd give that a quick note. So here's the examples. Good luck and happy studying.